Welcome back. And here we go for electrophilic aromatic substitution continued. And there's a lot going on in this one. Better take it slow. Remember, our motivation for this directing effects is when there's already a group on benzene, where does the next group go? So that's the question in the back of our mind throughout this whole discussion. So I'm going to call the group that's on benzene already the A group. And there's three categories of A groups that cover any possible group you can think of. We have groups that have a lone pair on the atom attached to the aromatic ring. So here's the aromatic ring. If you have a group with a lone pair, you want to take advantage of the fact that lone pairs can resonate with carbocations. Remember, the key intermediate on all of these pictures, all 9 of these, is a carbocation in the rate determining step. And that's all we need to focus on is the rate determining step. So if we have lone pairs, that's going to help carbocations. We want it to help the best way possible. Alkyl groups also help carbocations, but they can't resonate with them, like methyls and ethyls and isopropyls. They can hyperconjugate with carbocations if the carbocation is adjacent. Then we have the electron withdrawing groups without lone pairs on the attached atom. And in that case, you don't want that group anywhere near the carbocation. I mentioned I was having ill feelings when I saw the nitro group on the carbon with a carbocation, and hopefully that will be clear by the time we finish this page here. So I looked at the mechanisms for ortho, meta, and para. If you're going to do ortho, you can use this pair of electrons or this pair. And by way of resonance, you would get to these three resonance forms eventually, no matter which pair you chose. And to do meta, you would go with this pair of electrons or this pair and put the electrophile here. Let's just look at this one. And to go with para, you got to get the electrophile down here. So you do this pair of electrons. And what happens is you generate your cation. All three of the cations are resonance stabilized. So let's look at all the possible resonance forms. And here they are. You resonate the pi this way, and you get the cation down here. Resonate this pi this way, and you get the cation over there. And notice in the first resonance form, the cation is on the carbon with the A group. This is really good if the A group can stabilize carbocations. What two A groups can stabilize carbocations? Groups with a lone pair on the atom attached to the aromatic ring can resonate with the carbocation, and I showed that here. This is group 1, group with lone pair, resonating. This is a very nice resonance form. All the octets are full. Yes, you still have a charge. That's a bad thing, but all your octets are full. Here you had an octet violation with the carbocation. So that is a very nice position if the A group has a lone pair. If the A group is a hyperconjugator, which category has hyperconjugators in it? Well, our alkyl groups are hyperconjugators. So if we have a methyl or an ethyl, etc., up here, tert butyl, whatever, cyclohexyl, they will help. And this is a good way to do this mechanism. All right. Similarly, let's go straight down to para. You do the para mechanism. Your first cation is here, but the second one has the cation on the carbon with the A group. So anything we said up here has the same argument down here. A can stabilize the carbocation in the second resonance form. So that's a real good resonance form because A can really help out, whether it's by resonance or by hyperconjugation. So ortho and para happen together when we have a group that's type 1 or type 2. You want to take advantage of the fact that ortho and para put the cation on the carbon attached to the A group in this first resonance form here and down here in the second resonance form. If you do the meta mechanism, you'll see the cation never occupies the position of the carbon attached to A. So that is going to be your default choice when your A group destabilizes carbocations and can't even resonate with them with a lone pair. Even like a halogen can, even though it doesn't want to become a cation, can resonate. So halogens don't fit this category. They're in this top category. So things like nitro groups, though. Nitro groups. If A is a nitro, you want to definitely go meta, because that way you don't ever get the cation where the A group is. All right, so hopefully we understand that. And then we can look at a list of the groups. This next table is the most important table in chapter 22. It was a horizontal table in your textbook, but that was just to save space. I made it into a big potential energy diagram going top to bottom. And we have ortho-para directors. Those are the ones that can help carbocations. Why? Because if you put the next group ortho or para, one of the resonance forms has the carbocation on the carbon attached to the existing group. In this case, an amino group, and here an ether group, and here an amide or an ester. But remember, this is the amide attached by way of the nitrogen. This is the ester attached by way of the oxygen. Not to be confused by if we have an amide attached by way of carbonyl to the aromatic ring. That's a whole different category. So just seeing an amide doesn't make your decision for you. What atom is attached in the amide? If it's a nitrogen that has a lone pair, you're talking about ortho-para directing groups. If you have an amide where the carbonyl is attached to the benzene or the aromatic ring, then you're talking about meta, because you do not want a cation on the carbon attached to a carbonyl carbon, which is very positive. Okay, so these tell us that if any of these groups are on the aromatic ring, everything up here, then your products will be ortho and para. And there's a reason why para is usually major of those two. And the simple reason for that has nothing to do with this lovely page here. It has to do with the fact that if you put a group ortho, as it's coming in, if it comes in a little too close to the A, it bounces off and it doesn't make it. So it's got restricted access to this position. Can't come in hot from here. It'll bounce off the A. So if you go para, the A group is never in the way. If you go para, don't we have a description for things in the way, stopping things from approaching? We've been using ever since chapter 2. I think it started with a S, and there's hindrance involved. Oh, steric hindrance. So when you have ortho-para groups on benzene, para will usually be major and ortho will be minor. There's steric hindrance partially blocking the approach of the electrophile in the ortho position. No steric hindrance down here. So we have done 0 writing in this segment. Interesting. I think it's the longest we've gone. Now, why do we have halogens here? Why are they ortho-para directors? And why does it say this new word deactivating? Deactivating compared to what? Oh, deactivating compared to the baseline, which is having no groups at all. Normal benzene, where there's an H there. It'll be faster to put a new group on benzene than on a benzene that has a halogen. That's what this word says. Slower when there's a halogen already on benzene than when there's nothing on benzene. You still want to go ortho-para because your intermediates are, so say you had a chlorine on benzene. and you're reacting it with an electrophile, you want to go ortho like this and para like this. And you generate in your slow step here a great carbocation. I've seen better. It is next to an electronegative chlorine, which is not a great thing. But at least that electronegative chlorine can do this. Resonate. Fill that octet. Is it a great resonance form? Not really. Nope, it's not that either. And we don't have our new group on there. What happened? I went too far. I forgot to put my E on, didn't I? And you generated a chloronium. And you got your E up here. So that's a good thing. If you went meta, you couldn't do this. So you went ortho, and the resonance helps. Para, you initially get this species. And we don't have to draw all those resonance forms. We can show how the chlorine can help this cation right here. And you go para, you got your E here, and it can resonate with that cation. Look at that. It's a great cation. It's got full octets and all that. And we got our electrophile down there. So yeah, halogens, they slow things down because these are not very great cations. You don't typically like chlorine cations. But if you go meta, then you can't do this resonance with the cation at all. So chlorine's going to say, why'd you go meta? I can't help. So that's why chlorine and fluorine and bromine are ortho-para directors, but they slow things down. And these things slow things down a lot. Deactivating is bigger here because it's more deactivating. That's why it's lower on this speed chart. It's like a potential energy chart, really. Why are these so slow? Well, you've got a slightly positive carbon attached to a benzene, and then you're going to make the benzene into a carbocation in the mechanism. That's definitely slower than not having a positive atom attached. So the worst are at the bottom where we have, look, a carbon group, normally a hyperconjugator, but not this one, not with 3 chlorines attached, not with 3 fluorines attached. And trifluoromethyls are very common groups, especially in pharmaceuticals. You see a remarkable number of pharmaceuticals with trifluoromethyl. For reasons, I'll briefly mention. One reason you'll see a trifluoromethyl instead of a normal methyl is it prevents oxidation of the methyl group. You remember the benzylic position is rather susceptible to reactions. In biochemistry, this is true too, and a trifluoromethyl will generally shut those reactions down. So your drugs will last longer. Anyway, little sidetrack there. Nitriles attached to benzene. What does that mean? The next group's going to go meta. If there's a sulfonic acid or a sulfonamide attached, the next group's going to go meta. Let's get lots of practice with this. There's lots of practice in the book. We'll do different practice over here. So let's start with a benzene that already, well, no, let's review how to put groups on as we go too. How do you put this group on benzene? And then where's the next group gonna go? But I'm gonna come up with a whole handout here and then do the answers on the next page. And let's review old stuff, especially since this is the reason we learned the old stuff. How do I make that into this? A primary R group. 1, 2, 3, 4, 1, 2, 3, 4. Good. And then if I do another group, if I drew another group on this one, probably going to need a lot of heat on that one. And then if I do this reaction, what do we get here? And then if I put a nitro group on this one, where does it go? And I want two products. Major, minor. And then keep the game going. Something we learned recently. And from the major one, we'll put a third group on. Br2 Fe. And say, wait, he didn't teach us that. And you'd be correct. Okay. Question 1. How do you put a carbonyl on benzene? Should we go back on our notes today? I think we put a formyl group on earlier. It stopped right here. We put that group on. This is no different. It just has a propyl on there too. And yes, when it was a formyl group, we used formyl chloride. It's in your notes. When it's a butanoyl group, you use butanoyl chloride. And what was the catalyst that allowed this? It was aluminum. Remember, carbon groups, aluminum catalysts. That's a 3. Okay. What kind of a group is a carbonyl? Because when we go straight down, we have to keep in mind, we want to avoid any reaction whose rate determining step puts a cation here in any resonance form. That's what that whole page was 2 pages ago. Don't have the mechanism that puts the cation here. And that was the ortho-para mechanisms that both had one resonance form with a cation there. Do not go ortho or para when there's a group on benzene that has a positive or slightly positive charge. It's going meta. Your next group is going meta. So you can put it here or here. It doesn't matter. They're equivalent. And what's the new group when we use HNO3, H2SO4, and heat? Or just HNO3 and H2SO4? It's a nitro group. So let's do new molecules in purple. I want a meta nitro, and it doesn't have specifics that make you draw the nitro. So please, you don't have to draw out the nitro. Just remember the short form is NO2. And remember to put it meta. Put it in orange. And then a chapter 16 review reaction. What happens to ketones with zinc amalgam and HCl? I want to remind you that's called the Clemmensen reduction. And it reduces a carbonyl to a CH2. You can call a CH2 a methylene if you want to give it a name. So it'll just be a butyl group. Sounds familiar. There's a butyl group hidden to the top left of the screen right now. Clemenson will not touch a nitro group. Although reductions of nitro groups we have to talk about. I think I'll sneak it in at the end of this segment. It's that important. All right, so what's going on here? Carbonyl becomes CH2. This is not about electrophilic aromatic substitution. That benzene looks just, that's just sketchy. That double bond was there. Okay. How do you reduce it? I mean, the answer is already on the page, everybody. How do you get a carbonyl to be a CH2? You could use this one. Or you could review the other one we learned in chapter 16, the one where you had the mechanism and everything. It was hydrazine. This was the base version of the reaction. Hydrazine, hydroxide, excess, aqueous, and a little heat in there. That was called the Wolff-Kishner reduction, chapter 16. The main reason we learned it, if you look, we have a primary R group on benzene. Putting any R group on benzene is incredibly important. And what was the only group, carbon group, we didn't know how to put on? Well, we knew how to put a secondary or tertiary on. You started with alkyl chloride and you reacted with aluminum chloride and made a carbocation. And I'll just add a comment after the fact here. Secondary works as well. Caution though, slower. Secondary cations are slower. Notice there's no reaction if primary, because you can't make a cation there. You'd say methyl, worse story, right? No. Methyl's okay. You just use this as your electrophile. We saw that on the next page. Methyl groups on benzene, no big deal. You just use this as the electrophile. So we know how to put a secondary or a tertiary group on. We know how to put a methyl group on. We do not know how to put a primary group on. That's not 100% correct. You put a carbonyl on, and then you reduce it. There's a primary group. Put a carbonyl on and then reduce it. There's a primary group. Nice. And then I want you to look at the major and minor products from this reaction and then compare it to this reaction. What kind of a group is a carbon group? Is it a ortho-para-directing activator or a meta-directing deactivator? And the answer is an ortho-para with slight activation. Why? Because it helps carbocations. Why ortho-para? Well, it helps best when the cation's right there. The ortho and para mechanisms generate a cation where one of the resonance forms has the cation right here. Which one's major in an ortho-para reaction? Para or ortho? We have discussed this minutes ago. Okay, last segment. Which one do we go first for major? Ortho or para? And the answer is para for major because there's less hindrance down there. So we're going to have a para nitro group with a butyl upstairs. 1, 2, 3, 4. And nice nitro here. Oh, I want to put an orange to compare the other one. Why not? And ortho would be slightly lower amounts. Let's draw it a little better than that. Don't want to be lazy with benzene in chapters where benzene's the main topic. Ortho. Outside the box. 1, 2, 3, 4. So we've got all three. Meta, ortho, para. And a little comment about ortho and para here. Putting this group onto benzene was not a real expensive prospect. Butanoyl chloride's not that expensive. This reaction's pretty cheap. This one's pretty cheap, can be made cheaper if you do other methods that we don't need to learn. And even if you get a maximum of 40% yield on the ortho, this protocol going from here down to this minor is still the cheapest way to get the ortho product. And you just sacrifice half your benzene. Nothing's been expensive, so there you go. Even if that's your goal, you would follow all the steps to get here. And follow all the steps to get here, you just get a better yield. In meta, you want to reduce the carbonyl after you've put the second group on. Why? Well, the carbonyl is a meta director, and if you want the meta groups, you better put the meta director on, take advantage of its meta directedness, and then reduce it using either the Wolff-Kishner here or the, sorry, this is the Wolff-Kishner, or the Clemenson here. Both are good methods. And let's finish this off, and then we'll add one more late topic here. Put it in green. And we have to learn this one for sure. Learn everything for sure. You know that by now. But nitros, they're important by themselves, but amines are much more prevalent in biochemistry, aren't they? We have to learn how to reduce that thing from a highly oxidized nitrogen to a fully reduced nitrogen. So, and that's not an easy reaction. But before we move on, which of these two groups is the better one at helping cations? Well, this one hurts cations. It's got a plus on the nitrogen. This one helps cations. So what do you do when there's two groups on benzene and you want to put a third group on? You should be very interested in the answer to that question, because your retrosynthetic analysis on test 3 will be a benzene with how many groups on it? 3. So the question here is, where does the third group go is very important. Now, you've got a list, the most important list in the chapter. And it says, these are activators and these are deactivators. So when you have, the easy scenario is when you have an activator and a deactivator, which is our situation on our last page. The activator takes over. It's like the other guy is not even there. We want to take advantage of the activator's ability to stabilize a carbocation. And you can only do that by putting the third group, ortho or para, to the activator. And then you ignore the other group. Got it? Because that's the exact situation we have right here. I have an activator and a deactivator. This one needs to help. Now you say, oh, para is going to be major. Guess what, guys? Para is already taken. You can't put a new group there. So what's your only other option? You got it, ortho. So you're going to get an ortho product as your major product. Here's your boo. And ortho will be major. And what's your new group? When you use Br2 and Fe, and I didn't even talk about that. Aside. Bromine, very oxidizing. It's incredible. It'll take electrons from anything, especially a metal. You know iron likes to become oxidized. So even before this reaction starts, this has happened. And I'll try to make my inorganic chemistry friends happy. And even balance this for them. 2 of these. No, it's not going to make them happy at all. 3 of these makes 2 of these. And Oh, and bromine does not become boron either. My goodness. There you go. Hey, this is the cat. FeBr3 is just as good a catalyst as FeCl3. So what you would do is you'd use like 1.1 moles of Br2 and 1 mole of iron. And the 10th mole extra generates a catalyst. Sorry, you only need a 10th mole of iron because you only need a small amount of catalyst, right? So 1.1 moles of this, a 10th of a mole of this, you're going to make a 10th of a mole, roughly speaking, of this. I know I didn't account for balancing and stuff. So you're generating the catalyst, and then you have extra Br2 as the reactant. So you're going to put a bromine on. And major, there's no major and minor. Para is normal for a group like this, but it's taken. So you got to go ortho as your next best option. So that's where the third group goes there. Same argument up here. Which of these two is more important? It's the activating carbon here. And now you got a choice of ortho here or para here. Para is available. It's less hindered over here. Let's go there for our next group. And we don't even have that question here. We should have. It would have been a great question. Let's put a different group on. Let's put on Cl2 and iron. Same story about the catalyst. And what you would get is para if you ask for major only. And careful on tests. Sometimes I just say I want the major. Sometimes I want both. Good guideline is if there's only one box, I want the major. So you got your boo. And you've got your NO2 ortho. And the para was available, and you're going to get a chlorine. And this one down here is the end of chapter 21 reaction where you have a benzylic carbon, and you're making chromic acid here. Oh, yes, you have a good argument. I should have water in there. And you've got heat. You got to have the heat. That's benzylic oxidation. If you have one or more benzylic hydrogens, you will generate a benzoic acid derivative on the benzylic position, and the nitro group will still be there. And we'll finish this segment here by answering the question, how can we reduce a nitro group to an amino group? And there are 4 methods. And I want to make sure you know this is important. There's actually hundreds of ways, because the first one never works. That's how hard the reaction is. There's hundreds of ways because it's such an important reaction. You have to be able to do it. So on our next page, we're going to see how to do RNO2 becomes RNH2. Ready? You're responsible for 4 ways. Oh, opposite, right? RNO2. I'm having trouble drawing today. Okay, every day. How do you make a nitro into primary amine? And that's the big question mark, isn't it? Method 1. Okay, now we've done a lot of reductions. Nitro reduction would be a good title here. Nitro reduction. What reductions have we done? We started in chapter 6 where we reduced alkenes to alkanes using H2 and PT. That will work here if you use the right type of conditions. So write that one down. H2 PT. You'll generally have more success with that highly processed nickel. H2 nickel, rainy nickel it's called. It's highly refined and very porous, so it has a lot of surface area. Method 2. You try method 1, you can't get it to work. You got to move on. Method 2 is a good old powerful reducing agent we've seen multiple times. Lithium aluminum hydride. What's it always followed with? Every time. Some of you have learned the hard way that if you don't follow this, or if you don't separate it to 2 steps, you lose a quarter point. You always follow it with HCl. Those H's up here, those H's from HCl, well, one of them's from HCl for sure. That's method 2. In method 3, you tried the first 2, you couldn't get them to work. I know it's a lecture course, they always work. Yeah, good argument. You can use metallic tin and hydrogen chloride. Or you can use metallic iron and hydrochloric acid. There you go. I think that's a good list. I said we'd have 4. There's really 5 here if you count. And remember, 1 second there. Remember, this does reduce a lot of other things. So if you have a ketone in your molecule and you want to reduce an NO2, I would not be choosing method 2 unless you also want to reduce your ketone. This one's more selective. Wouldn't touch your ketone unless you had pressure. And then we have a question.
Can we use the sodium borohydride?
Sodium borohydride, 0 reaction. So just in review, sodium borohydride has very limited use. Do you want to do a quick NaBH4 since we're finished with it for the semester? This is the list, NaBH4 reactions. Do not add to this list. What you add will be wrong. We're going to take it back to chapter 6.
Demarcation.
Yes, see, good memory. We used NaBH4. And we got RH. We should have put those H's in blue. And then we're going to go to chapter 16 because that's the next time we saw it. So we'd say this is aldkete only. Don't add anything else to that list. H4. And that one, that's step 1. Step 2 is always HCl. It has that in common with lithium aluminum hydride. And you get the blue H here and the green H here. So you make an alcohol with a very strange O there. And the third thing we saw was nitriles. I want to make this comprehensive. Well, turned it off. Back to 2 steps. No, it's all blue. And everything turns blue. Both the new H's here and here. Blue. Both the new H's here and here. Green. They come from the green HCl. And that's all we saw sodium borohydride used for in this class and the previous class. Do not add to this list. I believe imines we did see. I'm not going to put imines here, but I want to remind you that an intermediate in this one is an imine, where you get a double bond to N, and then it reduces a second time. So, okay, I'll put imines here, since you asked. So, titles, nitriles, imines. I'll put enamines too. Look back in your notes, they're both in there. I only have an imine showing here. Similar results for both though. And you get the new H, better put your NABH4. And you get your new H there, that's green, because you got your new H here, that's blue. And that is actually a great spot to stop this segment. Reducing nitros, very important. These are the ways we've learned, and a little review of NABH4. Do not add to this list. We've been adding to that lithium aluminum hydride list nonstop. We will not be adding to this list. And I will see you guys and ladies on the other side of the break. Adieu.